You've been told a simple story about the universe your whole life, and it's wrong in ways that are honestly hard to stomach. In this video, I'm going to show you that the thing you think you live in is smaller, weirder, and way less final than anyone ever told you in school. We're going to strip away the comforting picture layer by layer until the word universe itself starts to feel too small for what's actually going on. By the end, you might still be sitting in the same room, but you will not feel like you're in the same reality. But before we continue, please subscribe to the channel to give your support. Let's continue. Right now, everything you have ever seen, every star, every galaxy photo, every deep space image, fits inside what's called your observable universe. That is not all of reality, it is just the region of space that has had enough time to send light to you since the Big Bang. Its radius is about 46.5 billion light years. In metric, that is about 4.4 times 10 to the power of 26 meters. In miles, that's around 2.9 times 10 to the power of 23 miles. These numbers are so large they stop feeling real, but the key point is simple. This bubble is finite, it has a size, and you are stuck inside it. The reason this bubble exists at all is the finite age of the universe. The Big Bang, or more precisely the hot early phase of our universe, happened about 13.8 billion years ago. Light and any signal has a maximum speed, so there is a maximum distance that light could have traveled since then. Draw a sphere around you with that distance, and that is your observable universe. Anything farther away than that, even if it is real, has not had enough time to send you any information. There is another twist. Space itself has been expanding while that light was on the way. So when you look at a very distant galaxy, you are seeing the light it emitted billions of years ago, when it was much closer. By the time that light reaches you, the space between you and that galaxy has stretched. The actual galaxy is now much farther away than the distance the light traveled. So even inside your bubble, you are not seeing the universe as it is now. You are seeing a stacked series of old snapshots frozen at different ages. The farther you look, the younger the universe you see. So here's the first hard question. If this bubble is just defined by how far light has traveled so far, why can't you eventually see everything if you just wait longer? This is where the speed limit of the universe collides with the expansion of space. There is a strict rule in physics. Nothing can move through space faster than light, about 300,000 kilometers per second, roughly 186,000 miles per second. That rule has been tested again and again, and nothing with mass has ever been seen to break it. So you might think, fine, if I wait long enough, light from any distant object will eventually reach me, as long as it is real. But that picture silently assumes that space itself is just a fixed stage. It is not. General relativity says that space can stretch and compress and curve, and that stretching is not limited by the speed of light. There's no law that says space cannot expand faster than this. The speed of light is a limit on how fast things move through space, not on how fast the distance between 2 points can increase if the space in between is expanding. Because of that, there are galaxies far enough away that, right now, their distance from you is increasing faster than light, not because they are zooming through space at that speed, but because the space between you and them is stretching so quickly. Light they send toward you gets dragged along by the expansion of space. In many cases, the expansion wins. The light never makes it to you. Those galaxies are outside not just your observable universe, but outside your future observable universe as well. No matter how long you wait, you will never see them. This gives you a very uncomfortable conclusion. There are real regions of the universe with real matter, real stars, maybe even real life, that are in principle cut off from you forever. They are not hidden by dust, they are not behind a wall, their information is just outrun by the expansion of the space in between. So then you might ask, if we are trapped like this, how do we know anything about the very early universe at all? What data do we actually have that reaches all the way back? The most important piece of evidence is the oldest light you can detect, called the cosmic microwave background. Right after the Big Bang, the universe was hot and dense, so hot that atoms could not exist. Everything was a plasma of free electrons and nuclei and photons. In that state, light could not travel freely. It kept scattering off charged particles, like trying to shine a flashlight into a dense fog. The light just bounced around. About 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with nuclei and form neutral atoms. When that happened, the fog cleared. Light could finally move in straight lines without constantly scattering. The radiation from that moment has been traveling ever since, stretched by the expansion of space from visible and infrared wavelengths down into the microwave range. Today, it shows up as a faint glow across the whole sky, with a temperature of about 2.725 degrees above absolute zero. Satellites like COBE, WMOP, and Planck have measured this glow with high precision. And what they found is striking. The temperature of this background radiation is almost exactly the same in every direction, equal to within about 1 part in 100,000. On top of that almost perfect uniformity, there are tiny hot and cold spots, just a few millionths of a degree different from the average. Those small differences are incredibly important. They're the fingerprints of tiny density variations in the early universe, regions that were slightly more dense than average and slightly less dense. Over billions of years, gravity amplified those small differences, pulling matter together, eventually forming galaxies, clusters, and the large-scale structures we see today. So the cosmic microwave background is doing two jobs at once. First, it confirms that our universe really did go through a hot, dense phase. Second, it gives us a baby picture of our observable universe, showing us how smooth and how slightly uneven it was when it was only a few 100,000 years old. Now, here comes the part where this becomes deeply suspicious. How can regions on opposite sides of your sky, separated today by more than 90 billion light years, have almost exactly the same temperature, when there was never enough time for light or any signal to travel between them before the cosmic microwave background was released? If you take the standard expansion without any special fix, you get the so-called horizon problem. Two distant regions in the early universe are so far apart that they could not have exchanged information, yet they look almost identical. It would be like cooking two separate pots of soup at opposite ends of the planet, never mixing them, never letting heat flow between them, and somehow they end up at exactly the same temperature down to 1 part in 100,000. That is extremely unlikely. The simplest way to solve this is to accept that what you are seeing now as your whole sky used to be a much smaller region that really was in contact with itself in some earlier phase that you cannot directly see. In that earlier phase, temperatures and densities could equalize, making everything smooth. Only later did that region expand to the enormous size that our observable universe covers today. And when cosmologists write down the equations for how space expands and fit them to the data from the cosmic microwave background and from galaxy surveys, those equations do not stop at the edge of your observable patch. They make no special feature there. The math that describes the expansion just continues. The most natural reading is space extends far beyond the part you can see, maybe unimaginably far. Put these pieces together and you get a sharp picture. You see only a limited bubble set by the age of the universe and the speed of light. Within that bubble, you see evidence of a hot early phase in the form of the cosmic microwave background, which is extremely smooth in temperature across regions that should never have been in contact under simple expansion. The equations that describe the expansion do not cut off at your horizon. All of this strongly hints that the part you can see is just a small portion of a larger whole. So the everyday statement, "this is the universe," is already misleading. What you actually mean is, this is the part of space-time that has managed to send light to me so far. Beyond that, the same laws of physics almost certainly continue, shaping regions of space and time that you will never observe directly. And this sets up the deeper question that drives the rest of the story. If even your observable universe is just a patch inside something larger, could that larger thing itself be only one region inside an even bigger, more complex structure, where space doesn't just expand, it goes into overdrive and creates entire new universes? The basic Big Bang picture, without anything extra, fails in two important ways, and both push you toward a more extreme early universe. First, smoothness. The cosmic microwave background is light that left the early plasma about 380,000 years after the Big Bang. Today, the regions that sent you that light from opposite sides of the sky are over 90 billion light years apart. With the speed of light as the limit, there was never enough time for any signal to travel between those regions before that light was released. So under simple expansion, they should never have been able to share heat or information. Yet their temperatures match to about 1 part in 100,000. That is the horizon problem. Regions that should be disconnected look almost perfectly coordinated. Second, flatness. On large scales, space behaves as if it is geometrically flat. In our best theories, any small mismatch between the actual density of matter and energy and a special critical density makes the universe curve, and that deviation from flatness naturally grows with time. But when you combine data from the cosmic microwave background, supernovae, and galaxy surveys, you find that any curvature today is smaller than roughly 1%. Trace that back, and the early universe had to be tuned extremely close to perfectly flat. That is the flatness problem. So the plain Big Bang needs initial conditions that are too special. It asks you to accept that the universe just started out almost perfectly smooth over huge distances that could not communicate, and almost perfectly flat with no physical process to set that up. You need one mechanism that can make distant regions uniform and drive space toward flatness without hand-tuning the start. That is what cosmic inflation is meant to do. Inflation says that very early on, before the hot phase you usually hear about, the universe went through a short period of very rapid expansion. Distances did not just grow, they doubled again and again in a tiny fraction of a second. In many models, this starts around 10 to the minus 30 seconds after the beginning and lasts for much less than a second. Yet in that interval, the size of a small patch can increase by a factor far beyond anything you see in the later universe. Start with a region that is small enough that light and particles can move across it many times, smoothing out temperature and density. Then let that region inflate. As it expands at this extreme rate, it stretches far beyond the range that light can cross afterward. A tiny, well-mixed patch becomes large enough to contain everything you now see as the observable universe. Points that are now separated by tens of billions of light years were once close enough to interact. The horizon problem is gone because those regions were in contact before inflation blew them apart. The same expansion dilutes curvature. Any initial bending of spacetime in that patch gets stretched away. After enough doubling steps, the observable part looks extremely close to flat, just as measurements indicate. In this view, flatness is not a fragile coincidence. It's the natural outcome of taking a small region and expanding it by a huge factor. The main test for this idea comes from the pattern of tiny hot and cold spots on the cosmic microwave background, captured in what's called the angular power spectrum. Satellites like WMAP and Planck measured how strong the fluctuations are at different angular scales on the sky. Inflationary models predict a specific pattern, fluctuations that are almost, but not exactly, the same strength on a wide range of scales, and a series of peaks and dips that come from sound waves in the early plasma. When you look at the data, you see that pattern. The spectrum is nearly scale invariant, which means the universe has structure on both large and small scales with similar amplitudes and only a small tilt. And the first big peak in the spectrum appears at an angular scale of about 1 degree on the sky. That angle corresponds to the largest sound waves that had time to travel before the plasma cooled. The position of that peak depends on the expansion history and the geometry. In a nearly flat universe with an inflationary past, it lands right around 1 degree. If space were strongly curved, it would be shifted. It is not. Other early universe scenarios have a hard time reproducing all these features at once without adding even more assumptions. Inflation, while not fully understood, lines up with the data in a way no other idea currently does. So, if you accept inflation, your observable universe grew out of a tiny, smooth, nearly flat patch that was blown up by a burst of ultra-fast expansion. But that same mechanism also opens a door to something stranger. In many concrete models, the rapid expansion is driven by a field sitting in a high-energy state. Quantum mechanics says that this field does not evolve in a smooth, identical way everywhere. It fluctuates. In some regions, those fluctuations push the field down, inflation ends, and the stored energy converts into a hot mix of particles and radiation. That's the start of a Big Bang-like phase in that region, with its own cosmic microwave background and galaxies to come. In other regions, the fluctuations push the field the other way, keeping it in the high energy state longer. There, inflation continues. Because inflation makes space expand faster than light can carry information, regions where inflation has ended can never completely catch up with regions where it is still running. While some pockets exit inflation and start normal cosmic evolution, other parts of space keep inflating and their volume grows enormously. This leads to eternal inflation. On the largest scales, space never stops inflating everywhere at once. Instead, it's always inflating somewhere, and within that inflating background, new bubble regions where inflation has ended keep forming. Each bubble has its own hot start, its own structures, and its own cosmic history. Your entire observable universe is one such bubble, one pocket where inflation shut off. That means that, even before you talk about other ideas like quantum many worlds or string theory, inflation alone already gives you a kind of multiverse, many bubble universes inside an ever-inflating background. And that pushes a sharper question straight at you. If you live in one bubble among many, formed by random quantum fluctuations, what does that do to the idea that there is one single shared universe whose boundaries match what you can see? The simple version of inflation, the one that just turns on, smooths everything, and turns off again, is actually not the full story. Once you take quantum effects seriously, it becomes hard for inflation to ever stop everywhere, and that changes what the universe even means. In many realistic models, the early universe is dominated by a high-energy state called a false vacuum. It is false because it is not the lowest possible energy. It's like a ball resting in a shallow dip on a hill, not down in the deepest valley. This false vacuum has a strange property. Its pressure is negative. In general relativity, negative pressure is not a detail. It actively drives space to expand faster and faster. Instead of gravity pulling things together, this vacuum energy makes space itself stretch at an insane rate. When false vacuum dominates, distances between points do not just grow slowly, they grow exponentially. That means in equal steps of time, they get multiplied by the same factor again and again. After a very small fraction of a second, a region that might have been microscopic can grow by a factor of 1 with 26 zeros after it, or even more. Remember, that is in meters, so we're talking about taking something far smaller than an atom and blowing it up to far beyond galaxy scales in less than a blink. Now add quantum mechanics. The field that carries this vacuum energy is not perfectly smooth. Quantum fluctuations kick it around. In some locations, those kicks help it slide or tunnel out of the false vacuum into a lower energy state. In others, the field gets pushed back up a bit and stays in the false vacuum. Wherever it stays high, the violent expansion continues. Wherever it drops low, inflation ends. Because a false vacuum makes space expand so fast, the total volume of space that is still inflating keeps growing, even though individual patches are constantly dropping out. For every region that exits inflation, many new inflating regions appear as the overall volume blows up. That is the core of eternal inflation. Once you get into a regime like this, the runaway expansion never ends everywhere at once. On the largest scales, the cosmos is always in this inflating high-energy phase somewhere. So then you have to ask, what actually happens in a patch that does manage to exit this state? What does it look like when a piece of the inflating background finally lets go? When a region leaves the false vacuum through quantum tunneling, you can think of it as forming a bubble of lower energy vacuum inside the higher energy sea. This is not a soap bubble in air. It's a region of space-time with different vacuum energy and different field configuration. Inside that bubble, the energy stored in the false vacuum gets converted into particles and radiation. This is called reheating. The result is a hot, dense state that looks a lot like the starting point of the usual Big Bang story, with a plasma of particles, light, and fields all crammed together. So, a Big Bang in this picture is not something happening in empty nothing. It's the local end of inflation, a phase transition of the vacuum itself. Inside the bubble, normal expansion takes over. The hot plasma cools, atoms form, the cosmic microwave background is released, and galaxies eventually grow. Outside the bubble, inflation is still running, space is still stretching at crazy rates, and more bubbles are forming elsewhere. If this is really going on, you might expect to see some sign of other bubbles in our sky. So you have to ask, where would those signatures show up and what do we actually see? If another bubble universe had collided with ours at some point in our past light cone, it could leave a mark in the cosmic microwave background. The collision would inject energy and distort the local geometry, which might show up today as circular features, unusual temperature patterns, or asymmetries in the CMB map. People have searched for this. Teams have taken the data from satellites like WOMAP and Planck and looked for statistically unusual circles or spots that might fit the profile of a past bubble impact. So far, nothing has been found that the community accepts as solid evidence. There are anomalies in the CMB, odd cold regions, slight alignments, but none of them rise to the level where you can confidently say this is a collision with another universe. That already tells you something. If bubbles exist, then in our observable patch at least, either we haven't had a major collision or the signatures are too subtle or too rare to stand out above the random noise and cosmic variance in the data we have. At the same time, the very inflation models that match our observations of the CMB, the large-scale structure of galaxies, and the near flatness of space tend to give eternal inflation automatically when you include quantum fluctuations. You don't bolt the multiverse on as a separate idea. It drops out of the same mechanism you already used to fix the horizon and flatness problems. That doesn't prove eternal inflation is real, but it means you can't dismiss it as a wild extra. It's woven into many of the models that already work best. So now you have a serious conceptual shift to deal with. Your entire visible universe, with its roughly 2 trillion galaxies inside the observable volume, its stars, its black holes, its planets, could be just one bubble, one local region in a much larger inflating spacetime that's constantly spawning more such regions. Inside different bubbles, the details can change. The fields that set particle masses and interaction strength can settle into different states. The amount of dark energy can be different. The pattern of initial fluctuations can vary. That means you can have many universes in the sense of large, internally connected regions with each its own effective laws of physics and its own cosmic history. Your bubble is just one selection out of an uncountable set of possibilities. In that picture, when you say reality, you're not talking about a single connected block of space-time with one fixed rule set. You're talking about one pocket in an eternally growing structure, where most of space is still in a high-energy phase you'll never see, and where new Big Bang-like regions are constantly starting up elsewhere forever out of your reach. And that immediately raises the next sharper question. If there are many bubbles and they can have different properties, what actually sets those properties? Is there some deeper menu of possible universes that inflation is sampling from? Or are we missing an even more fundamental layer that decides which kind of cosmos can exist at all? You already have eternal inflation giving you many bubble universes. The next step is to ask what actually decides what kind of physics each bubble gets. What sets the particle types, their masses, the strength of forces, the amount of dark energy? That's where string theory and the so-called string landscape enter, and things get a lot more extreme. The starting point is the idea that the particles you know, electrons, quarks, photons, are not tiny points, but tiny vibrating strings. Their typical length is around the Planck scale, about 1.6 times 10 to the power of minus 35 meters. For scale, a proton is about 10 to the power of minus 15 meters. So you're talking about something 20 orders of magnitude smaller than that. At those scales, quantum gravity effects become important. So if you want one framework that includes both quantum mechanics and gravity, this is where you have to work. When people write down string theory consistently, they run into a hard fact. The math doesn't naturally close in only 3 space dimensions plus time. Depending on the specific version, you end up with 10 or 11 dimensions total. The three spatial directions you move through, left, right, forward, back, up, down, plus one time dimension are just the extended ones. The rest are extra spatial directions that are not visible to you in everyday life. You experience four-dimensional space-time because the other dimensions are not large and open in the same way. So the obvious question is, if there really are extra dimensions, why don't you bump into them? Why don't they show up in any experiment you've done? The simple answer inside string theory is compactification. The extra dimensions are not infinite like the ones you walk through. They're wrapped up into tiny shapes with sizes on the order of maybe 10 to the power of minus 33 centimeters. That's so small that even the most powerful particle accelerators on Earth, which probe down to around 10 to the power of minus 18 meters or so, can't even begin to touch them. At human scales, and even at atomic scales, these extra directions are effectively hidden, but they're not irrelevant. How those extra dimensions are curled up matters a lot. They can form different topologies and geometries, often very complicated ones called Calabi-Yau spaces. The shape, the volume, and the way fields thread through those shapes determine key low-energy properties of the world you see. Change the compactification, and you change the effective physics in the large extended dimensions. That means that different ways of curling up the extra dimensions can give you different particle spectra, different particle masses, different coupling strengths between forces, and different values for the vacuum energy, which you see as the cosmological constant or dark energy. In other words, each choice of compactification is like a different recipe for building a universe from the same underlying string theory. Now, here's the key point. When people count how many distinct, internally consistent compactifications there might be, they do not get 10 or 100. They get numbers like 10 to the power of 500 or even larger. That is a 1 with 500 zeros after it, a ridiculous number of possible vacuum states, each with its own effective laws of physics. That collection of possibilities is what people call the string landscape. You might then say, fine, this is all theory space, but does any of it touch reality? Is there any way to check if this is more than clever algebra? Right now, you do not have a clean, direct signature of string physics. You cannot look at a detector event and say, that bump is a vibrating string. But any theory that claims to be a complete description of high-energy physics has to satisfy some hard constraints. At particle colliders like the Large Hadron Collider, we have smashed protons together at energies of several trillion electron volts. We have mapped out the known particle spectrum, found the Higgs boson, and looked hard for signs of new physics such as supersymmetric partners or extra heavy gauge bosons. Whatever string theory looks like at low energy, it has to reproduce the standard model spectrum we actually see, at least up to those energies. Gravity has been tested down to distances of about 10 micrometers, which is 10 millionths of a meter, or about 4/10,000ths of an inch. At those scales, Newton's inverse square law still holds to high precision. That rules out many naive extra dimension models where gravity suddenly changes at, say, a millimeter. String-inspired scenarios have to be compatible with these null results. On the cosmology side, any candidate theory has to match the observed amount of dark matter and dark energy, the pattern of fluctuations in the cosmic microwave background, the success of Big Bang nucleosynthesis, and the late-time large-scale structure. String-based models can be built that fit these data, but you can also build non-string models that fit them, so this is a consistency check, not a unique proof. So at the moment, string theory is less a single sharp prediction engine and more a huge framework that contains an enormous menu of possible universes. That sounds like a weakness, but in the context of eternal inflation, it becomes a feature. Inflation can generate many bubble universes. The string landscape says there are many different vacuum states those bubbles can fall into. Put them together and you get a picture where different bubbles in the inflating background realize different points in the landscape, each with its own low-energy physics. Then you hit one of the worst mismatches in all of physics, and the string landscape plus inflation give you a way to even talk about it. The problem is the cosmological constant, or vacuum energy. Observations tell you that the dark energy density in your universe is tiny but not zero. Written as a mass density, it's roughly 7 times 10 to the power of negative 30 grams per cubic centimeter, or about 10 to the power of negative 26 kilograms per cubic meter. That is the equivalent of a few hydrogen atoms worth of energy, spread out over a volume the size of a room. It's very small, but over cosmic distances, it dominates the dynamics of the expansion. If you take quantum field theory seriously and calculate the vacuum energy by summing up all the modes of all fields up to some high cutoff, you get numbers that are larger than the observed value by factors of 10 to the power of 60, or even 10 to the power of 120, depending on the details. That is not a small mismatch. It's arguably the worst prediction in all of physics. In the string landscape picture, most possible vacuum states do have huge vacuum energies. In those states, the expansion is so violent that matter cannot clump into galaxies. Either everything rips apart too fast or it collapses too quickly, depending on the sign of the cosmological constant. Only a tiny fraction of vacua have vacuum energy small enough, and with the right sign, to allow a long-lived, slowly expanding universe, where structures can form and persist for billions of years. Combine that with eternal inflation, and you get a specific kind of explanation. Eternal inflation spreads you over the landscape, producing bubbles that realize many different vacuum states. Most of those bubbles never form galaxies, stars, or anything we would call observers. You only find yourself in a bubble where the parameters land in the narrow range that allows complex structures and long-lived chemistry. In other words, you don't see a random vacuum. You see a vacuum selected by the condition that observers exist to measure it at all. That's anthropic selection. This is not emotionally satisfying. It feels like giving up on a clean, unique derivation of the constants from first principles. Instead, you get a statistical story. Your universe is one rare case in a vast population of possibilities, and you're biased to see those rare cases because only those can host something like you. But if eternal inflation is real, and if something like the string landscape is real, this combination might be exactly what reality does. The values of the constants you measure would then be environmental facts about your particular bubble, not universal laws carved into the foundation of everything. And that pushes the pressure up even further, because if your laws of nature can vary from bubble to bubble, you have to ask a much harder question. Is the three-dimensional world you move through really the full stage, or is it just one type of object, one kind of brane floating in a higher dimensional space where even more drastic variations of physics are possible? You think you move in 3 dimensions, and that's the whole story. Up, down, left, right, forward, back, and that's it. But some models say your entire universe is just a 3-dimensional sheet sitting inside a bigger space you never see. In these models, that sheet is called a brane, short for membrane. Your everyday world, the one where electrons orbit nuclei, quarks bind into protons and neutrons, and photons carry light, is confined to this 3D brane. All the familiar particles and forces of the standard model are stuck here. They cannot move off the brane. They behave like they're glued to it. Gravity is different. Because it's a property of space-time itself in general relativity, it can spread into extra dimensions. So in a brane world picture, you live on a 3-dimensional surface embedded in a higher dimensional bulk, and gravity is the one interaction that is allowed to leak off your sheet and explore the bulk. You feel it mostly on the brane, but its field lines can extend into the extra directions. Now, that sounds like a random sci-fi upgrade, so why would physicists take it seriously at all? What problem is it trying to solve? One big puzzle is why gravity is so weak compared to the other forces. Take a small magnet and a paperclip. The magnet wins against the entire pull of Earth on that clip. That means the electromagnetic force from a tiny magnet easily beats the gravitational pull from a whole planet. In particle physics units, this weakness shows up as the gap between the Planck scale, where gravity becomes strong, and the electroweak scale, where the weak and electromagnetism unify. The ratio is huge, many orders of magnitude. That gap is the hierarchy problem. The Randall-Sundrum models attack this using a warped extra dimension. Instead of extra dimensions that are just flat and compact, they considered a 5-dimensional spacetime, 4 normal dimensions plus 1 extra spatial dimension, where the geometry is strongly curved in that extra direction. You can picture 2 branes in this setup, one where gravity is naturally strong and another where we live, where the effective strength of gravity is suppressed by the warp factor. In that scenario, the true fundamental scale of gravity in the bulk can be close to the other forces, not insanely weaker. The reason you experience gravity as weak on our brane is that the warp of the extra dimension dilutes it here. The metric, the thing that measures distances and times, has a factor that shrinks energy scales as you move along the extra dimension. By the time you get to our brane, the Planck scale looks huge and gravity looks feeble. So you pushing a 1 kilogram mass with your hand and only feeling a small resistance might not mean gravity is intrinsically weak. It might mean you are sitting on a brane where gravity's true strength has been redshifted down. That is an attractive idea on paper, but you immediately have to ask, where are these extra dimensions in the data? Why don't any experiments see them? People have tested Newton's law of gravity down to distances of about 10 to the power of -4 meters, around 0.004 inches. At those scales, the force still falls off like 1 over distance squared, with no sign of sudden changes or leaks into extra dimensions. That rules out simple models where gravity suddenly spreads into large extra dimensions at a millimeter scale or so. Brane world models like Randall-Sundrum are designed to evade this by making the extra dimension effectively hidden by the warp. The deviation from normal gravity at short distances can be made small enough that current tabletop experiments cannot see it, but that also means it's hard to confirm directly. On larger scales, any modified gravity theory has to reproduce a long list of successes from standard general relativity plus dark matter and dark energy. Orbital motion in galaxies has to match what we see. Gravitational lensing, where mass bends light from background galaxies, has to agree with observations. The pattern of acoustic peaks in the cosmic microwave background, those precise wiggles in the power spectrum, is very sensitive to how gravity behaved in the early universe. So far, the simplest 4-dimensional picture with general relativity, cold dark matter, and a cosmological constant fits all of this extremely well. Any brane world model that survives has to be tuned to behave almost exactly like that at the scales we have measured. So you end up in an odd situation. Brane worlds are not excluded, but the allowed versions are subtle. They may show up only at energies higher than what the Large Hadron Collider can reach, or at distance scales smaller than current gravity experiments can probe, or in regimes we have not observed yet, like extreme black hole environments. For now, they remain consistent possibilities, not confirmed facts. If you accept that branes might be real objects in a higher dimensional bulk, then there is no reason to stop at one. Just like there can be many 3-dimensional slices inside a larger volume, theory allows many branes with different properties coexisting in the bulk. Each brane could carry its own version of the standard model, its own particles, its own constants. To an observer made of those particles, that brane would look like an entire universe. Branes might be parallel in the extra dimension, or curved around, or even intersecting. If 2 branes pass close to each other or collide, energy can be transferred between them. In some models, events like that are used to explain a Big Bang, not as a creation from absolute nothing, but as the result of a brane interaction in the bulk that dumps energy onto our brane and heats it up. In that picture, your entire cosmos, with billions of galaxies stretching over tens of billions of light years, is just one 3-dimensional sheet in a larger, higher dimensional structure, with other sheets that you can never see directly sitting next to you in directions your senses do not access. Gravity might be the only messenger that can probe between branes, and even then, only weakly. Put that next to eternal inflation and the string landscape. You can have a bulk with extra dimensions populated by multiple branes. On those branes, inflation can run and end, creating bubble universes. The string landscape can decide the vacuum state and low energy physics for each brane or bubble. You are not just in a big space-time, you are in one specific layer with one specific vacuum on one specific brane. And there is still another blow coming. All of this, extra dimensions, bubbles, branes, still assumes there is one classical space-time with one history. But in quantum mechanics, even that can fail. So you have to ask, if space itself can be many-layered, could the history running inside it be branching all the time, so that even within one bubble, on one brane, there is not one universe, but countless parallel versions of events playing out? You live in a world that runs on quantum rules, but your experience never shows you those rules directly, and that mismatch will never go away. At the fundamental level, quantum mechanics says a particle doesn't have to be in one definite state. An electron can be in a superposition of here and there at the same time. A photon can be in a superposition of going through slit A and slit B at once. The math that describes this is a wave function, and that wave function always evolves smoothly in time according to one clean linear equation. If you just follow that equation, superpositions never collapse, they just keep evolving. But when you actually do an experiment, you don't see both at once. You set up a detector and you see one spot light up, not a blurry half here, half there event. You measure a spin and you get up or down, not some mix. So standard textbooks bolt on an extra rule. When you measure, the wave function suddenly collapses into a single outcome with a certain probability. Before the measurement, multiple outcomes are possible. After the measurement, one is real, the others are gone. That collapse rule is not part of the elegant time evolution. It's a special, vague instruction. When something counts as a measurement, do this different thing. Where exactly does a measurement start? At the detector, at the computer, in your brain? The theory doesn't say. That fuzziness is the measurement problem. You have a mathematical object that happily lives in many states at once, and a world that never shows you that directly, and a patch that tries to connect them by saying, and here, it just collapses. So here's the hard question. What if you stop giving yourself that escape hatch? What if you refuse to add collapse as a separate law and just let the standard quantum equation run on everything, including you and your measuring devices? That is exactly what Hugh Everett did in the 1950s. His move was brutally simple. Take the wave function seriously, everywhere, all the time, and never collapse it. If the wave function says a system is in a superposition of outcomes, then that is the real state. When a measurement happens, the system being measured, the measuring device, and your brain all get entangled, and the linear evolution doesn't pick one branch, it produces a superposition of branches. In one branch, the detector shows result A, and there is a version of you who has seen A. In another branch, the detector shows result B, and there's a version of you who has seen B. Those two branches quickly become decoherent, which means all the quantum phases that could make them interfere get scrambled and effectively lost to you. From inside one branch, it looks like the wave function collapsed onto your outcome. In reality, under this view, nothing collapsed. The full wave function just became a sum of you saw A plus you saw B plus maybe many other options. So you do not get a superposition of you felt both results. You get multiple copies of you, each in a different branch, each with a consistent story where only one result ever happened. That is the many worlds interpretation. There is one master quantum state for the whole universe, and every time a quantum event with several possible outcomes happens, the state branches into non-communicating pieces that all continue to exist. That sounds extreme, so why would anyone take it seriously instead of just sticking with the collapse story and moving on? The main reason is this. Quantum mechanics works absurdly well, and it has never given you a clear signal that it breaks down and needs collapse. You can calculate the magnetic moment of the electron using quantum field theory and get an answer that matches experiments to more than 10 decimal places. You can predict how atoms absorb and emit light and how semiconductor devices will behave. And you can build lasers and GPS and MRI machines on top of those rules. The linear unitary evolution part of the theory has survived every test. On top of that, experiments keep pushing quantum behavior to larger systems and longer distances. Entangled photons have been sent over tens of kilometers, tens of miles, with their correlations intact. Large molecules containing thousands of atoms have been put into states where their center of mass behaves like a quantum wave, showing interference patterns when you send them through gratings. Experiments keep trying to see where macro objects start behaving purely classically, and every time the boundary moves upward. As far as we can tell, if you could isolate a bigger system well enough from its environment, you could maintain superpositions for it too. We do not have direct observational access to other branches of the wave function. By construction, once decoherence has done its work, branches no longer interfere and you cannot send a signal between them. But the core quantum formalism that predicts all the things we can test is the same formalism that, if you apply it without collapse, gives you many worlds. MWI basically says, stop adding a vague extra rule that never shows up in the clean equations and accept that the full math is telling you something about reality itself. So if you go down that road and you take many worlds seriously, what counts as real now? What is the universe in this picture? Here, the universe is not a single four-dimensional spacetime with one fixed history. It is the total quantum state, a wave function defined on a huge configuration space that tracks all degrees of freedom. That wave function evolves smoothly according to the quantum rules, and because it constantly encounters situations where different outcomes are possible, it constantly branches into decohered pieces. Each piece is what you would normally call a universe, with its own consistent history and its own version of events. Your entire life, from your point of view, is one trajectory inside one branch. Every time a quantum event with multiple outcomes happens in a way that could affect your macroscopic world, the state splits. There is a version of you who gets one result, a version who gets the other, and so on. You only ever experience one thread, but the full physical description contains all of them. This is a very different kind of multiverse from the ones we talked about before. Eternal inflation and brane worlds and the string landscape all add more regions of spacetime, more bubbles and branes and vacua, often with extra dimensions. Many worlds does not need any of that. It takes whatever spacetime you already have and says quantum evolution alone already gives you a branching collection of universes, one for each decohered history. And these ideas can stack. You can have eternal inflation creating many bubble universes in an inflating background. Each bubble could have its own vacuum from the string landscape, maybe sitting on its own brane in a higher dimensional bulk. Inside each bubble, quantum events keep branching that bubble's history into many worlds branches. So even if you somehow picked one bubble, one set of laws, one brane, you would still not have a single unique universe. You would have an entire family of parallel histories running in that same overall setup. So now you are not just small in space, living in one observable patch of a bigger cosmos. You are also small in the space of possible histories, living on one branch of a much bigger quantum tree. And there is still another twist coming, because even this tree of universes might itself be a derived picture, not the base layer. There are hints that space-time and gravity might be a kind of output of something even more abstract, something that looks a lot more like information theory than like geometry. You already know black holes are extreme, but the numbers behind them say something even stranger. They say that your idea of how much stuff can fit in a region of space is probably wrong. Take a black hole with the mass of the sun. General relativity says it would have a radius of about 3 kilometers, around 1.9 miles. That's tiny compared to the actual sun, which has a radius of about 700,000 kilometers. But the really important thing here is its entropy, basically the number that measures how many microscopic states it could have, how much information it can store. For a solar mass black hole, that entropy is roughly 10 to the power of 77, a 1 with 77 zeros after it in pure number units. Now, you might expect that if you double the amount of space, you double the number of possible internal configurations. That's how normal systems work. A box of gas has entropy that scales with its volume. But for black holes, that's not what happens. When you calculate the entropy carefully, you find it scales with the area of the event horizon, the surface, not the volume inside. Double the radius and the area grows like the radius squared, not the radius cubed. More mass, bigger radius, bigger area, and the entropy tracks that area. The clean way to say it is the maximum information you can cram into a region without collapsing it into something worse is proportional to the boundary of its area measured in Planck units. A Planck area is tiny, around 10 to the power of -70 square meters. You can tile the event horizon with a huge number of these patches, and each patch can store about 1 bit of information. That is the picture that drops out of the math. So for a black hole, it's as if all the information about everything that has ever fallen in, all the invisible internal degrees of freedom, is encoded on the surface, on the horizon. The volume doesn't get its own independent budget. That is already a major hint that your naive 1 bit for every tiny chunk of volume picture of reality doesn't survive in quantum gravity. Then people like Gerard 't Hooft and Leonard Susskind took a sharp step. They asked, if black holes behave like this, why should they be special? Why not apply the same logic to any region of space? That's the holographic principle. The claim is not that space is literally fake, it's that the maximum amount of information that can fit in a given region without forming a black hole scales with the area of its boundary, not its volume. Take a sphere with a radius of 1 light year. Your everyday intuition says if you increase the volume, you can always fit more independent bits of reality inside. Holography says no, there's an upper bound, and that bound goes like the area of the sphere in Planck units. This is a radical constraint on what a fundamental theory of gravity and quantum mechanics can look like. It's saying that your continuous three-dimensional volume is not a place where you can independently flip an arbitrary bit at every tiny point. The Hilbert space, the space of possible states, is finite and area limited once gravity is in the game. That still sounds abstract, like an information theory slogan, until you get a case where you can actually show how it works in full detail. That's where ADS-CFT comes in. In certain versions of string theory, you can set up a universe with a specific kind of negative curvature, called anti-de Sitter space. That's the ADS part. In that space-time, gravity lives in a bulk with, say, 5 dimensions, 4 of space and 1 of time. On the boundary of that bulk, you can define a quantum field theory with no gravity, living in 1 fewer spatial dimension. That's the CFT, conformal field theory. The ADS-CFT correspondence says these two descriptions are exactly equivalent. Every physical process in the bulk involving gravity, black holes, strings, and so on has a dual description on the boundary in terms of ordinary quantum fields without gravity, and vice versa. Compute something in the bulk, and you can translate it into a statement about correlation functions on the boundary theory. Compute something in the boundary theory, and you can read it as a statement about geometry and dynamics in the bulk. This is not a loose analogy. It's a duality with tons of detailed checks. People have computed thermodynamic properties, correlation functions, transport coefficients, and they match on both sides. From the perspective of information, this is a clean, working example of holography. A higher dimensional gravity world is fully encoded in a lower dimensional quantum theory at its edge. So you end up with a serious statement, at least in these ADS contexts. Everything that happens in a volume with gravity can be rewritten as something happening on a lower dimensional, gravity-free boundary. The interior and the boundary are two ways of packaging the same physics. You don't live in an anti-de Sitter universe, though. Observations tell you that your cosmic expansion is accelerating due to dark energy. That gives you a geometry more like de Sitter space, with positive curvature in the time direction. We do not yet have a clean, fully worked out de Sitter holography at the same level as ADS-CFT. The mathematics is harder, and the dual field theories are not as well understood. Still, the success of holographic dualities in the ADS case is a strong hint. It suggests that gravity and space-time might generally be emergent, that they might arise from some underlying degrees of freedom that look more like quantum bits organized in a lower dimensional structure, or in a purely abstract network. In that view, geometry, distances, and maybe even time are not fundamental. They are effective descriptions that show up when you look at the underlying data in a certain way. If that's right, then your three-dimensional space plus time is one representation of a deeper thing. The everyday picture you have of objects moving around in a volume is a high-level description, like the way a computer screen shows you windows and icons, while the real work is happening down at the level of bits and operations. The true constraints on what can happen, how much stuff can exist, and how information flows are set by the lower dimensional or more abstract structure underneath. You can hook this back into everything else you've seen. Eternal inflation and the string landscape give you many possible vacua and bubbles. Brane worlds give you higher dimensional structures where our observable universe is just one slice. Many worlds says even one bubble's history branches into many quantum outcomes. Holography adds another layer, telling you that even the familiar space-time those stories live in might not be the base layer. It might itself be a way of encoding some more fundamental information. So now the term the universe has drifted even further from meaning the whole of reality. At best, it's the effective three-dimensional bulk description you get from one particular holographic encoding for one region with one rule set. And the next step is to ask a very specific question. If space and gravity are emergent like this, what does that do to your picture of the universe's overall shape and structure? Can space itself be finite, looping, or twisted in ways that your local bulk-based intuition completely misses? You've probably heard people say the universe is flat, and it sounds like a final answer, job done, story over. But that word hides a big loophole in what space might actually be. Flat is about geometry, not about the overall shape of the universe. Geometry tells you what happens locally. In flat space, small triangles have angles that add up to 180 degrees. Parallel lines stay the same distance apart. Light rays that start off straight don't curve just because of the background space. Measurements of the cosmic microwave background and how galaxies cluster all say that on scales we can see, the geometry of space is very close to flat. Any curvature, positive or negative, is tiny, less than 1% over the size of the observable universe. Topology is different. Topology is the way space is connected globally. You can have a perfectly flat two-dimensional surface that extends forever, like an ideal plane. You can also have a perfectly flat two-dimensional surface that is finite but has no edge, like a torus, which you can picture as a square whose opposite sides are glued together. Locally, both are geometry flat. Small triangles behave the same. Globally, one goes on forever, the other loops back on itself so that if you keep walking straight, you eventually come back to where you started. Extend that idea to 3 dimensions. You can have a 3-dimensional space that is flat and infinite, the standard infinite box picture most people carry around. But you can also have a 3-dimensional space that is flat and multi-connected, where going in one direction long enough brings you back from another side, with no edges, no boundaries, and still no local curvature. That's a 3-torus version of space, and there are many more complicated examples. So flat does not tell you if the universe is infinite or finite, or if it loops around in weird ways. It just tells you that in the region you can probe, straight lines behave as they do in ordinary Euclidean space. To know the topology, you need global information. The catch is you only see a finite patch, your observable universe, a ball with a radius of about 46 billion light years, something like 4.4 times 10 to the power of 26 meters. So the question is, with that limited view, how could you possibly tell whether space outside that patch is infinite or whether your patch is sitting inside some looping, twisted structure? One clever way is to use the oldest light you can see and look for repeated patterns, like echoes of the same region showing up in different directions. If space is topologically compact on a scale not that much larger than the observable universe, light can wrap around it. Think of a photon leaving a point in the early universe. In an infinite, simply connected space, it just moves out in one direction forever. In a multi-connected space, that path can effectively come back from another direction after traversing the loops in the topology. By the time that photon reaches you, it might have gone around the universe one or more times. Now think about the cosmic microwave background. What you see in the sky is radiation coming from a spherical surface around you, the surface where the universe first became transparent, around 380,000 years after the Big Bang. If space is small enough and wraps around, that sphere can intersect itself. The same physical patch of plasma could send you light along different routes. On the sky, that would show up as pairs of circles in different directions with matching patterns of hot and cold spots along their rims. People have actually searched for those circles in the sky. Teams took the high-resolution maps from WeMap and Planck, which showed temperature fluctuations down to scales of arc minutes, and ran algorithms to compare circular strips around the sky, looking for pairs of circles with the same pattern within the limits of noise and foreground contamination. If the fundamental domain of space, the size of the repeating cell in a multi-connected model, were smaller than or comparable to the observable radius, you would expect to see at least some of these matched circles. So what did they actually find? The short answer is no convincing, statistically strong pairs of circles that look like clear duplicates of each other across the sky. That doesn't prove that space is infinite and simple, but it does rule out a whole class of small universe models, where the loops are shorter than or similar to the diameter of the observable universe, more than 46 billion light-years. That means you don't see your own tail in the data. You are not obviously seeing the same region of early plasma from two sides. But that still leaves a lot of room. You could live in a 3 torus that is 10 times the size of the observable universe in each direction. You could live in a much more complex, compact manifold with no simple symmetries. Many of those shapes would produce no detectable matching circles in the data we have, yet they would still be finite, multi-connected spaces. Locally, everything would look flat and normal. Globally, the map of where you are would be completely different from the picture in your head. The deeper point is not about one specific shape. It's about how fragile your intuitive ideas of here and there really are. If your observable patch sits inside a space with non-trivial topology, then the straight-line path you imagine from point A to point B might actually thread through a structure that loops around and glues back on itself. Space could be finite but without edges. It could identify points that look far apart in the naive picture. It could create ghost copies of structures at different locations and times, even though they are really the same underlying region. Add that to everything else you've already seen. The observable universe is only a bubble inside a larger inflating spacetime. Eternal inflation and the string landscape say there may be many bubbles with different physics. Brane world models put your whole cosmos on one sheet among many in higher dimensions. Many worlds says even within one bubble on one brane, you have branching histories. Holography says the entire three-dimensional bulk might be a way of encoding lower dimensional information. Now, topology tells you that even the basic assumption, space is a simple infinite box, is just one option among many. And the data already hints that if there is weirdness, it lives on scales at or beyond what you can see. So you're left with a space that might loop, twist, or close on itself beyond your horizon, and with a picture of the universe that's already heavily restricted to one region, on one sheet, in one branch. And on top of all of that, there's a blunt numerical fact we have not used yet. Most of the energy budget inside your observable bubble is not in the stuff you see at all. Almost everything, by mass and energy, is in dark components that don't glow, don't show up directly, but control how structure forms and how the expansion runs. If the shape of space can hide from you, and the fundamental layer might be holographic, what does it mean that roughly 95% of your cosmic contents are dark and invisible? How deep does the hidden structure go when even the inventory of matter and energy is mostly unknown? How do you trust your picture of the universe when every time you measure carefully, almost all the mass and energy turns out to be missing from the picture? Start with something simple. How fast stars move in a galaxy. In a spiral galaxy like the Milky Way, you can measure how quickly stars orbit around the center at different distances. You do this by looking at the Doppler shift of their light in kilometers per second. If most of the mass is in the bright central region and in the visible disk, then stars far out, tens of thousands of light years from the center, should orbit more slowly. The farther out you go, the lower the speed, like planets in the solar system, where Neptune moves slower than Earth. That is not what you see. When astronomers measure rotation curves, they find that beyond some inner region, the orbital speed of stars stays almost flat. Out at 20, 30, 40,000 light years, stars are still going about 200 to 300 kilometers per second, roughly 450,000 to 670,000 miles per hour, and the curve does not drop the way simple gravity from visible matter says it should. If only the stars and gas you see were providing the gravity, those outer stars would not be bound tightly enough. The galaxy would not hold together over billions of years. It would slowly fly apart. So you're forced to choose. Either you add more mass that does not shine, so the outer stars feel a stronger gravitational pull than their orbit suggests from visible matter alone, or you change the law of gravity on these scales. When you look at many galaxies and see the same pattern again and again, the simplest and most consistent move is to add an unseen component, dark matter, that forms an extended halo around each galaxy and dominates the mass budget. Then you zoom out and look at bigger structures, clusters of galaxies. Now you have multiple independent ways to weigh them. You can count the galaxies and estimate their mass. You can measure the hot gas between galaxies with X-ray telescopes. That gas can be tens of millions of degrees, so you know what gravitational field is needed to hold it in. And you can look at gravitational lensing, how the cluster bends light from even more distant background galaxies, distorting their apparent shapes and positions. When you do this for objects like the bullet cluster, you get a sharp result. The hot X-ray gas, which is normal matter, is slowed down and lags behind during a collision of two clusters because it collides and shocks. The lensing, which maps the total mass, is centered not on the gas, but on regions that have passed through each other almost unaffected, where the galaxies are. That tells you the dominant mass is in a component that barely interacts except through gravity. It doesn't collide or shock like gas. You need about 5 to 6 times more mass in this collisionless component than in the normal matter you can see. Then you zoom out and look at bigger structures, clusters of galaxies. Now you have multiple independent ways to weigh them. You can count the galaxies and estimate their mass. You can measure the hot gas between galaxies with X-ray telescopes. That gas can be tens of millions of degrees, so you know what gravitational field is needed to hold it in. And you can look at gravitational lensing, how the cluster bends light from even more distant background galaxies, distorting their apparent shapes and positions. When you do this for objects like the bullet cluster, you get a sharp result. The hot X-ray gas, which is normal matter, is slowed down and lags behind during a collision of two clusters because it collides and shocks. The lensing, which maps the total mass, is centered not on the gas, but on regions that have passed through each other almost unaffected, where the galaxies are. That tells you the dominant mass is in a component that barely interacts except through gravity. It doesn't collide or shock like gas. You need about 5 to 6 times more mass in this collisionless component than in the normal matter you can see. Then put all of that together with the cosmic microwave background. The detailed pattern of temperature fluctuations on the sky tells you how much normal matter and dark matter the early universe had, because normal matter and radiation interact and oscillate, while dark matter mostly sits in gravitational wells. The heights and positions of the acoustic peaks in the CMB power spectrum give you a ratio of normal to dark matter that matches what you infer from galaxy rotation and cluster lensing. You get a picture where only about 5% of the cosmic energy budget is normal matter. Protons, neutrons, electrons, everything you see. About 27% is dark matter. The rest, about 68%, is something even stranger. That last component shows up when you look at the expansion history of the universe. For a long time, people assumed the expansion was slowing down because gravity pulls matter together. But in the late 1990s, when teams used Type A supernovae as standard candles to measure distances to faraway galaxies, they found the opposite. For a given redshift, those supernovae were dimmer than expected, which means farther away than they should have been in a slowing universe. The expansion rate is increasing, not decreasing. The universe is accelerating. To fit the supernova data plus the CMB plus the large-scale distribution of galaxies, you need a component that acts like a uniform energy density filling space with negative pressure. In Einstein's equations, that negative pressure drives accelerated expansion. The simplest implementation is a cosmological constant, a property of the vacuum itself. When you fit the data, you get a vacuum energy density of about 10 to the power of minus 26 kilograms per cubic meter, equivalent to just a few hydrogen atoms worth of mass per cubic meter of space, but spread everywhere. That small density, multiplied over enormous volumes, dominates the fate of the expansion. So your current best fit model, the one called lambda cold dark matter, says this: roughly 5% normal matter, 27% cold dark matter, 68% dark energy. Everything you see, stars, gas, dust, planets, you, is in that 5%. The rest does not emit light, does not absorb light, and has only been detected through its gravitational effects and its influence on expansion. You need both components to make sense of the data. Dark matter explains how galaxies and clusters form and hold together. Dark energy explains why the universe is accelerating and why the geometry looks so close to flat. You can play games with modified gravity, with inhomogeneous models, with other tweaks, but you keep running into the same thing. It is extremely hard to match all the observations at once without adding new physics in the form of hidden sectors or vacuum energy. What does that tell you about the depth of the structure you live in? Dark matter could be new particles that sit in a hidden sector, maybe with their own forces and interactions you barely feel. They could form their own bound structures, their own versions of atoms and cooling, and maybe even complex systems, all almost completely invisible to you. Dark energy could be a fundamental property of the vacuum, or the effect of a slowly rolling field, or a sign that your four-dimensional description of gravity is only an approximation to some higher dimensional or emergent dynamics. In brane world pictures, for example, the effect of dark energy on our brain might come from the geometry of the bulk, or from energy trapped on nearby branes. Either way, the picture is not one clean universe made of one kind of stuff obeying one simple rule. It is a hierarchy. Luminous matter is a trace component sitting inside dark matter halos. Those halos live in a space-time whose large-scale behavior is dominated by dark energy. That space-time might have non-trivial topology. It might be one bubble in an eternally inflating background. It might be tied to one point in the string landscape, maybe realized on one brane in a higher dimensional bulk. And the history running inside that bubble could be branching constantly in the many-world sense, while the whole thing is encoded holographically at some boundary. So the more accurately you measure, the less your everyday language, the universe, looks like a fundamental object. You are looking at a visible surface effect of deeper structures, and the numbers say that surface is a small correction, not the main term. And there is still one more place where this shows up brutally. If dark energy really behaves like a constant vacuum energy, it will drive the expansion to keep accelerating, pulling distant regions permanently out of contact. If gravity and space-time break down at very high densities, the Big Bang might not have been a true beginning, just a transition. So you have to ask, if the current universe is one phase in a larger story, could there have been a contracting universe before this one, or multiple cycles, or repeated bangs triggered by deeper dynamics you haven't built into the model yet? When you take the equations of general relativity seriously and run them backward in time, they drive you straight into a wall. If you follow the expansion of the universe back, the scale factor shrinks. Everything gets denser and hotter, and at some finite time in the past, the math says densities, temperatures, and curvature go to infinity. That point is what the classical theory calls a singularity. Space and time themselves hit a beginning, where the equations stop making sense. But infinity is usually a red flag, not a literal description. In physics, when you hit an infinity, it usually means you push the theory beyond the regime where it's valid. General relativity is a classical theory of space-time. It does not include quantum effects. Near the Planck scale, where lengths are around 10 to the power of minus 35 meters and times are around 10 to the power of minus 44 seconds, you expect quantum mechanics to matter there. So that singularity at time equals 0 is almost certainly telling you need a quantum theory of gravity there. It is not telling you that the universe really did something infinitely sharp and magical. So the obvious question is, what happens if you put quantum gravity into the story and then run the clock back toward the would-be Big Bang? In loop quantum gravity and its simplified cosmology version, you try to quantize space-time itself. Areas and volumes come in discrete chunks, in units set by the Planck area and Planck volume. Space is no longer a smooth continuum at all scales. It's more like a network of finite elements. When you translate that into a cosmological setting, you get modified equations for how the scale factor evolves when densities get extreme. Those modified equations do something important. As the density approaches a critical value, around 10 to the power of 94 grams per cubic centimeter, quantum geometry effects kick in and act like a repulsive force. Instead of gravity just pulling everything together harder and harder, you get an effective push that resists further compression. The result is that the contraction of the universe stops at a minimum size and then reverses. You don't get a singularity, you get a bounce. In that picture, what you usually call the Big Bang is not the absolute beginning of everything. It is the transition between a previous contracting phase and the current expanding phase. The Big Bang becomes a big bounce. Before the bounce, the universe was large and contracting. At the bounce, quantum gravity effects took over at extreme densities and forced the turnaround. After the bounce, the universe expands, cools, and eventually looks like what you see today. Other approaches, like some versions of string cosmology, do something similar with different machinery. They also try to avoid literal singularities, replacing them with transitions or bounces where new physics becomes dominant. Then you have another category of models that reuse some of the brane ideas you saw earlier. In ekpyotic and cyclic brane models, your observable universe lives on a brane embedded in a higher dimensional bulk. There is at least one other brane in that bulk. The key idea is that these branes are not static. Under certain conditions, they move toward and away from each other in the extra dimension. When two branes approach and collide, the energy of the collision heats the branes and gives you something that, from the point of view of an observer stuck on one brane, looks like a hot Big Bang. You get a burst of radiation and matter, expansion begins, structures form. Over a long time, the expansion slows, maybe reverses, and the branes start to move back together. After a long cycle, they collide again, injecting energy again, triggering another hot phase. In that scenario, what you think of as the universe goes through repeated cycles. Heat up, expand, cool, contract, repeat. The word ekpyotic comes from a Greek word for conflagration, the idea of periodic cosmic fires. Depending on the details, these models can be strictly cyclical, with many similar cycles, or they can have variations between cycles. All of this sounds like it could replace the simple, one-off beginning picture, but you can't just pick any bounce or cycle you like. You're constrained by what you actually see in this phase. Any bounce or cyclic model has to reproduce the near-scale invariant pattern of fluctuations in the cosmic microwave background. You need small, almost but not exactly equal amplitude perturbations over a wide range of scales, with the right slight tilt and with the right phase relationships between peaks. Inflation does this naturally by stretching quantum fluctuations. Bounce and ekpyotic models have to find other mechanisms that generate similar perturbations during contraction or near the bounce, and you don't do that without running into instabilities or conflicts with other constraints. You also have to pass the Big Bang nuclear synthesis test. The abundances of light elements, like helium and deuterium, are set in the first few minutes of the hot phase. They match the standard hot Big Bang predictions very well. Any bounce or cyclic scenario still needs a hot, dense period with the same temperature and density conditions to get those yields. You can't mess with that without breaking agreement with observed element abundances. And there's another subtle constraint. We don't see obvious memory from previous cycles in our observable patch. If the universe had many prior cycles with leftover black holes, gravitational wave backgrounds, or weird large-scale features, some of that might leak into the current cycle. So far, the sky we see looks like a clean start around 13.8 billion years ago, with no clear signatures that scream, this is at least the 10th round. Any viable cyclic model has to explain why previous cycles don't leave obvious scars in our CMB and large-scale structure. When you stack all those requirements, standard lambda cold dark matter with inflation is still the simplest model that passes everything. It gives you the right CMB spectrum, the right element abundances, the right structure formation, the right expansion history, with a relatively small set of parameters. Bounce and cyclic models can be built that fit a lot of the data, but they often need more tuning or extra ingredients. So right now, the data do not force you to abandon the standard "our expansion phase started about 13.8 billion years ago" picture. But they also don't prove that this was the absolute beginning. Quantum gravity ideas with bounces and brane collisions and cyclic models show you logically consistent ways that a Big Bang could be a transition, not a start, a local event in a longer sequence. That pushes your language to change again. Saying the universe began 13.8 billion years ago might really mean the current expanding phase began then, with the door still open to a contracting phase before that, or to previous cycles, or to more complex histories in a higher dimensional setting. And once you admit that what you call the beginning might be just a local reset in a deeper process, it becomes natural to ask something even more uncomfortable. If our entire phase could be one step in a longer chain, could the precise rules and constants for this phase be set by something outside it? As if our physics is a configuration chosen or generated by a more fundamental layer. The way a program's behavior is fixed by a higher level code that never appears on the screen. You keep finding the same numbers, the same patterns, the same behaviors, no matter where or when you look. And that consistency is exactly what pushes some people to ask if you're living inside a rule set. Take physical constants. The fine structure constant, the number that measures the strength of electromagnetism, is about 1/137. People have checked whether it changes over billions of years and billions of light years by looking at absorption lines in the light from distant quasars and comparing them to what you measure in labs. Within tight error bars, it's the same. The spectra of atoms, the way electrons jump between levels, the way light interacts with matter, all of it matches the same formulas across cosmic distances. That's not how a messy, random system looks. It looks like one rulebook is being applied everywhere in your observable bubble, with no patches, no local exceptions. Gravity follows the same equation in the solar system and in distant galaxies. Quantum mechanics gives the same interference and entanglement behavior in labs on Earth, and in the statistics of photons that left ultra-bright objects billions of years ago. The whole thing behaves as if some underlying code is enforced with ruthless consistency. So you're forced to ask a blunt question. Is that just what a lawful physical universe looks like? Or is it what a well-run program looks like? Now link that to another line of thought, the digital versus analog debate about space-time itself. If space-time is truly continuous, then you can keep slicing distances and times into smaller and smaller pieces forever. But several approaches to quantum gravity hint that this isn't how the base layer behaves. At the Planck scale, lengths around 10 to the minus 35 meters, some models say areas and volumes come in discrete chunks. Loop quantum gravity, for example, gives you quantized areas and volumes. Other ideas suggest a fundamental lattice or network structure underneath the smooth metric you use in general relativity. If there is a smallest meaningful length and time, if you can't define anything below around 10 to the minus 35 meters or 10 to the minus 44 seconds, then spacetime is not an infinitely detailed canvas. It's made of finite units. You can think of those units as pixels or cells, finer than any microscope you could ever build, but still discrete. Once you start talking that way, it's natural to ask whether the full evolution of the universe, step by step, could be seen as a computation running on those units. You don't have to jump straight to, "we are in a computer," to see the connection. A discrete underlying structure with update rules is exactly what you use in cellular automata, in lattice simulations of quantum fields, in all sorts of numerical models. If the base layer of reality looks like that, the line between fundamental physics and information processing starts to blur. If that's more than an analogy, there ought to be some way, even in principle, to see traces of the underlying discreteness. So people have tried to think of tests, something like lattice artifacts in the universe. One idea is that if spacetime has a preferred grid, then particles moving at extreme energies might feel that grid. High-energy cosmic rays, the most energetic particles we've ever seen, could show slight directional preferences or energy cutoffs that deviate from what a perfectly continuous Lorentz invariant spacetime predicts. Another idea is that if spacetime is built from discrete elements, the noise in very sensitive systems like interferometers might have a particular signature, a non-random spectrum that shows an underlying structure. So far, none of these searches have found decisive evidence. High-energy cosmic rays obey the expected relations within our current measurement limits. Precision tests of Lorentz invariance, the principle that physics is the same for all observers moving at constant velocity, have not shown clear violations. Noise in advanced detectors, like those used for gravitational waves, looks messy and technical, not like a neat, universal footprint of space-time granularity. Right now, your best working models still treat spacetime as smooth at the scales you can probe, and they work extremely well. If there is an underlying lattice, it's hidden very deeply or its effects are extremely subtle, so you don't have a clean yes or no on discretization, much less on simulation. But that leaves the core conceptual point on the table, and this is where the component of a larger reality idea takes a very literal shape. If the simulation hypothesis is true in a hard sense, then what you call the universe is a subsystem inside a larger information processing reality. The parameters you measure, like the fine structure constant, the masses of particles, the ratio of dark matter to normal matter, the value of dark energy, are parameters in that higher level system. The equations you write down, the standard model, general relativity, quantum mechanics, are effective rules implemented within that subsystem. The initial conditions, the specific state at the start of your observable phase, are part of the input. In that view, the outside is not more space, not another bubble, not another brane. It's a higher level structure with its own rules, where running universes is just one possible operation. Your whole cosmic history, from the hot early phase to galaxy formation, to you watching this, would be one trajectory through the state space of that system. You don't have empirical proof of that. It might be untestable if any attempt to detect the edges of the simulation is either filtered out or impossible by design. Philosophically and scientifically, that's a problem. A hypothesis that can never make different predictions from ordinary physics is not very useful as a theory. But even if you treat it as a speculative framing, it fits the pattern you've been seeing. Over and over, the thing you thought was the whole turns out to be one layer. Your observable universe is one bubble in an inflating background. That bubble might realize one vacuum choice in a vast string landscape. It might live on one brane among many in a higher dimensional bulk. Its history might be one branch in a many worlds wave function. Its spacetime might be one holographic encoding of more fundamental information. Its topology might be one way of stitching space together among many. Its contents are mostly dark sectors you barely understand. Its beginning might be one bounce in a longer chain. And in the simulation framing, all of that sits inside a deeper information processing structure whose full rules you never see directly. So you end up with a sharp, disturbing question. If everything you observe is generated by relatively simple rules plus a lot of time, what does that combination actually build on the largest scales? What kind of patterns and structures does this rule set produce when you let it run for billions of years on top of dark matter, dark energy, and quantum fluctuations? When you actually chart where galaxies are in space, on scales of hundreds of millions of light years, you don't get a random sprinkle, you get structure on a ridiculous scale. Astronomers map galaxy positions using big surveys, measuring redshifts for millions of galaxies and turning angle on the sky plus redshift into a three-dimensional map. When you plot those points, you see that galaxies line up along long filaments and sheets, with huge underdense regions in between called voids. This is the cosmic web. A typical unit here is the megaparsec. 1 megaparsec is about 3.26 million light-years. Filaments can run for tens to hundreds of megaparsecs, so you're talking about structures that are hundreds of millions of light-years long, which is on the order of 10 to the power of 21 to 10 to the power of 22 kilometers. That's hundreds of quintillions of kilometers for a single thread in this web. Closer in, galaxies cluster into groups and clusters that sit at the nodes where filaments intersect. Between those filaments and nodes are voids that can be tens of megaparsecs across, huge regions with almost no galaxies. So on the largest scales, you don't see a smooth fog or a random scatter, you see a very particular pattern with a typical spacing and a clear network. The obvious question is whether this pattern is telling you about some hidden rule beyond gravity, or whether it's exactly what you would expect from simple laws applied over a very long time. To answer that, people run n-body simulations. You start with a big box of space, maybe hundreds of megaparsecs on a side. You fill it with billions of particles, each one standing in for a clump of dark matter. You give those particles initial positions and velocities based on what you know from the cosmic microwave background, a universe that is almost uniform with small density fluctuations of roughly 1 part in 100,000, with a specific spectrum of fluctuation strengths as a function of scale. Then you let the system evolve under gravity, plus the effect of dark energy in the background. You include the measured fraction of dark matter versus normal matter and the dark energy density that accelerates expansion. You don't need to program in filaments by hand. You just say, here are the rules, Newtonian gravity or general relativity in an expanding universe, and these starting conditions, and then you numerically integrate those equations forward in time. What comes out of those simulations looks like the observed universe. Over billions of years, regions that are a little denser than average pull in more matter and grow, while slightly underdense regions evacuate. Small clumps merge into bigger ones. Filaments form as matter flows along preferred directions, and clusters grow where filaments intersect. Voids expand and get emptier. When you compare the web of dark matter in the simulation to the map of galaxies in real surveys, the match is striking. The large-scale pattern, the distribution of filament thicknesses, the sizes of voids, the way clusters connect, all line up when you choose the right cosmological parameters. Then you can go further. You can add gas physics, cooling, star formation, and feedback from supernovae and black holes to see how galaxies populate the dark matter skeleton. You still find that the overall arrangement is set by the dark matter and the initial quantum fluctuations from the early universe. Baryons, the normal matter, fill in that scaffold. On top of this web, there is another very specific imprint that links the present structure back to the early plasma, baryon acoustic oscillations. In the early universe, before recombination, normal matter and radiation were tightly coupled. Density perturbations in that plasma set up sound waves, regions where pressure and gravity traded off, creating oscillations in density that expanded outward at a fixed speed. When the universe cooled enough for atoms to form and photons to decouple, those sound waves froze in. The maximum distance they had traveled by then is called the sound horizon. Today, that sound horizon shows up as a preferred scale in the clustering of galaxies. When you measure how likely it is to find pairs of galaxies separated by different distances, you see a small excess at around 150 megaparsecs, about 490 million light-years. That bump is the fossil of those early sound waves, the baryon acoustic oscillation scale. This BAO feature is useful in two ways. First, it's a standard ruler. You know its physical size from early universe physics, so by seeing how large it looks at different redshifts, you can infer how the expansion of the universe has stretched distances over time. Second, it's a direct link between the tiny fluctuations in the cosmic microwave background and the huge structures you see now. The same physics that set up ripples in the plasma left measurable fingerprints in where galaxies ended up. Put all this together, and you get a very sharp statement. Starting from a nearly uniform universe with small quantum origin fluctuations and evolving under gravity with dark matter and dark energy, you naturally get the large-scale web you observe. You don't need extra forces or ad hoc patterns. The rules are simple. Gravity pulls, expansion stretches, dark matter dominates the mass, dark energy controls the late-time expansion. And out of that, over billions of years, the complex network of filaments, sheets, and voids emerges. That is exactly the kind of behavior you expect from a system where simple underlying laws generate complex patterns at higher levels. You see it in fluid dynamics, where simple equations for velocity and pressure give you storms and vortices. You see it in reaction diffusion systems, where simple chemical rules give you stripes and spots. Here, on cosmic scales, you see it in the way quantum fluctuations plus gravity and expansion generate the cosmic web. So the universe you see is not a random mess. It's one particular large-scale pattern produced by a specific rule set and a specific set of parameters, run for about 13.8 billion years. If you had different parameters, different amounts of dark matter or dark energy, or a different initial fluctuation spectrum, you would get a different web, or no web at all. And that brings you to a tight conclusion. The structures you see now are emergent behavior. They sit on top of a deeper layer of rules involving gravity, quantum mechanics, and the contents of the universe. But those rules themselves might not be fundamental. We already have hints from holography, from loop quantum mechanics, from tensor network ideas that space-time and gravity may emerge from something even more basic, something that looks less like geometry and more like quantum information and entanglement. So, the obvious next question is, if even space-time might be built from something deeper, what does that do to the whole idea of the universe as a basic object? Does it just become one user-facing interface built on top of quantum degrees of freedom that don't look like space or time at all? You've been treating space and time as the stage where physics happens, but the two main theories you use don't even agree on what that stage is made of. On one side, you have general relativity. It treats space-time as a smooth, continuous fabric. Matter and energy tell space-time how to curve. Curvature tells matter how to move. Black holes, gravitational waves, the expansion of the universe all come out of this picture. There's no smallest chunk of space in this framework. You can zoom in forever, and the equations still pretend to work. On the other side, you have quantum mechanics and quantum field theory on top of it. Those say that energy levels are quantized, that fields come in discrete excitations, that you have uncertainty relations, and that empty space is full of fluctuations. When you combine quantum mechanics with special relativity, you get quantum fields that live on a background spacetime, but you do not let those fields curve space. You just feed them a fixed geometry. Both theories work incredibly well in their own domains. General relativity nails gravity on large scales, in weak and strong fields. Quantum theory nails everything microscopic, from atoms to particle collisions. But take them both into the same extreme regime and they start giving nonsense. That regime is where you cram so much mass into such a small region that you hit Planck-scale densities. Roughly, take something like 10 to the power of 38 kilograms and stuff it into a volume of order the Planck length cubed, around 10 to the power of minus 105 cubic meters. There, quantum fluctuations of spacetime itself become huge, and classical curvature blows up. General relativity predicts singularities, infinite curvature. Quantum field theory assumes a fixed background and cannot handle that feedback. That's the quantum gravity regime, and you don't yet have a single finished theory that handles it cleanly in all situations. So you have to ask, what does space-time look like when you stop pretending it's infinitely smooth and finally quantize it? Loop quantum gravity is one attempt to answer that directly. Instead of taking space-time as a continuous manifold and then putting quantum field on top, it tries to quantize geometry itself. In LQG, areas and volumes are not arbitrary real numbers. They come in discrete units, like energy levels in an atom. The basic objects are spin networks, graphs whose links carry labels related to angular momentum. The areas of surfaces and volumes of regions, when you compute them in this framework, can only take values in discrete sets, with minimum non-zero units set by the Planck scale. A Planck area is on the order of 10 to the minus 70 square meters. At those scales, space-time is no longer a smooth fabric. It's more like a network of finite patches. You can't divide a surface into smaller and smaller real pieces forever. You eventually hit the smallest chunks. When you translate loop quantum gravity ideas into cosmology, you get loop quantum cosmology, a simplified model where the universe as a whole has a discrete geometric structure at tiny scales. In these models, when you run the equations back toward what would classically be the Big Bang, something important happens. As the density approaches a critical value, quantum geometry corrections modify the effective gravitational dynamics. Instead of gravity pulling harder and harder with no limit, you get a repulsive effect that kicks in at ultra-high density. That repulsion prevents the scale factor from going all the way to zero. The universe contracts down to a minimum size, then bounces and re-expands. The classical singularity is replaced by a bounce, and the Big Bang becomes a transition instead of a breakdown. Similar ideas show up in attempts to resolve black hole singularities. When you treat the interior with LQG-type methods, you can get scenarios where the classical singularity is removed, replaced by a region of high but finite curvature, and maybe a transition to another phase of spacetime. That's one direction. Another direction takes holographic hints seriously and ties space-time to quantum entanglement itself. In certain holographic setups, there's a precise relation between how much entanglement there is between different parts of the boundary theory and the geometry of the bulk spacetime. The Ryu-Takayanagi formula, for example, says the entropy of entanglement between a region of the boundary and the rest is proportional to the area of a minimal surface in the bulk that hangs off that region. Change the entanglement pattern and the bulk geometry changes. People have pushed that further using tensor networks, graphical structures that represent how quantum states are built from simpler pieces. Some of these networks, like Mira, naturally lay out in a way that looks like a discretized spacetime with extra directions. When you arrange tensors to reproduce certain entanglement patterns, the graph you draw starts to look like a slice of a curved space. Distances and curvature emerge from how strongly and how widely the degrees of freedom are entangled. The core idea is sharp. Geometry is not fundamental. Entanglement is. The amount of entanglement between different degrees of freedom dictates the effective distance between them. Highly entangled regions are close. Weakly entangled regions are far. If you change the entanglement structure, you warp the emergent geometry. In the most extreme case, if you remove entanglement between two sets of degrees of freedom, the corresponding regions of emergent space literally disconnect. Space falls apart into separate pieces. So in these pictures, space-time is not a background you put quantum fields on. It is an emergent large-scale description of something more basic, which is a web of quantum degrees of freedom and their entanglement. Gravity, in turn, becomes a manifestation of how this emergent geometry responds when you change the energy or the state of those underlying degrees of freedom. If you accept that possibility, the hierarchy shifts again. The universe, in the sense of a four-dimensional space-time with matter and fields, is no longer the base layer. It's a higher-level phenomenon, built from more fundamental quantum informational building blocks. Seen that way, three-dimensional space plus one time dimension is like an interface, a way of organizing and visualizing underlying data. Particles moving, fields oscillating, gravitational waves propagating, those are all effective descriptions that work at large scales, for observers made of those same emergent degrees of freedom. But they obscure the fact that at the deepest level, what exists might be a gigantic quantum state in some abstract Hilbert space, with entanglement patterns and algebraic relations that do not look like geometry at all. Now, link this back to everything else. Eternal inflation and the string landscape already pushed you to think about many vacua and many bubbles. Brane worlds added higher dimensional structures. Many worlds added branching histories. Holography told you the bulk might be encoded on a boundary. Quantum gravity and emergent spacetime tell you even bulk and boundary might be emergent from something more primitive, something closer to pure information. At this point, the phrase "our universe" has been demoted several times. It's one emergent spacetime with one set of effective laws in one region realized by one configuration of more fundamental degrees of freedom. It is not the top of the stack. So the only reasonable next move is to look at what your best current instruments are actually doing at the edges of this picture. Because every time you build a new kind of telescope or detector, you expose a new regime. And so far, every new regime has revealed structures you did not expect. If space-time and gravity are emergent from something deeper, the next generation of observatories is not just adding detail, it's stress testing the very idea that this emergent layer is the final one. Right now, the universe is not just a story in equations, it's an active crime scene, and our newest instruments keep turning up clues that don't quite fit the neat picture. The James Webb Telescope is one of the sharpest tools you've got for looking back into the first billion years after the Big Bang. By staring at tiny patches of sky in infrared, it sees galaxies whose light left them when the universe was less than 400 million years old, at redshifts above 10. In human terms, you are seeing baby pictures taken when the universe was still under 3% of its current age. What's weird is how grown up some of those babies look. A number of candidate galaxies at high redshift seem surprisingly massive and bright for such an early time. If their inferred stellar masses and star formation rates hold up, that means either stars formed more efficiently than many models assumed, or feedback processes work differently. None of this kills the standard cosmology. It does force people to adjust the details of how quickly you can build up big, complex structures so early. At the same time, an entirely different kind of telescope has opened a new channel: gravitational wave detectors. Since 2015, observatories like LIGO and Virgo have been measuring tiny changes in the length of their arms caused by passing ripples in spacetime. These ripples are generated when heavy objects like black holes and neutron stars orbit each other and merge. The waves carry information about the masses and spins of the objects, about the distance to the source, and about how space-time responds to extreme dynamical curvature. Gravitational waves are valuable because they barely interact with matter. A wave can travel for hundreds of millions or billions of light years without being absorbed or scattered. That means they deliver a clean signal from regions that photons can't escape, like the final orbits of two black holes about to merge. You're not inferring what happens there by modeling, you're directly listening to the sound of space-time ringing. The first detections were binary black hole mergers, each with tens of solar masses, colliding and forming a new black hole. Later, LIGO and Virgo picked up binary neutron star mergers, where two ultra-dense neutron stars spiral together. Those events have rich physics. The gravitational wave signal encodes the deformability of neutron star matter, which tells you about the equation of state of matter at densities far beyond what nuclear experiments on Earth can reach. The electromagnetic counterpart, gamma rays and optical afterglows, tells you how heavy elements like gold and platinum are synthesized. Then comes an extra twist. When you see both gravitational waves and light from the same event, you can turn the system into a standard siren. Here's how that works. The gravitational wave signal from a binary neutron-star merger has a characteristic shape. From its amplitude and frequency evolution, you can infer the luminosity distance to the source directly from general relativity, without needing the usual cosmic distance ladder that uses parallax, then Cepheid variables, then supernovae, step by step. Meanwhile, the light counterpart lets you identify the host galaxy and measure its redshift, how much the universe has expanded since the waves were emitted. Combine distance from the gravitational waves with redshift from the light, and you get a direct measurement of the Hubble constant, the current expansion rate of the universe. As you collect more of these events, you can cross-check the Hubble constant you infer from the local universe against the value inferred from the early universe via the CMB. Any persistent mismatch could signal new physics in expansion, dark energy, or gravity itself. So far, the uncertainties are still large, but the method is clear. Standard sirens give you a way to stress test the entire expansion history and to look for cracks in the LCDM model without relying on the same assumptions as traditional methods. Now zoom out and look at the pattern. Every time you open a new observational window, the universe throws you something you didn't predict in detail. X-ray astronomy unveiled hot gas in galaxy clusters and violent accretion disks around black holes. Gamma-ray astronomy found bursts so intense they outshine entire galaxies for brief moments. Radio astronomy revealed jets, pulsars, and relics of past explosions. Neutrino detectors see particles streaming from the sun and from supernovae, carrying information that photons can't. Gravitational waves now show you mergers, and maybe, in the future, backgrounds from the early universe itself. Every time you look in a genuinely new way, you find that reality is using more of the rule set than you realized. When you stack everything from the observable bubble and inflation to branes, to many worlds, to holography, to emergent spacetime, to dark sectors, to possible bounces and simulations, and then you add this constant pattern of surprises from new observations, a clear theme emerges. The thing you casually call the universe is one specific realization of some deeper structure, not the whole story. So the final step is to put all of these threads together and ask, if all these multiple verses and emergent layers can coexist, what actually remains solid? What can you still call real without qualification? And how far down the stack of reality goes before the word universe stops being useful? By now, you've seen so many ways reality can be bigger than the universe that it's easy to lose track of what's actually on the table. So let's line it up clearly. You've got inflationary bubbles from eternal inflation, entire regions where inflation ended and a hot Big Bang phase started, like the bubble you live in now. You've got the string landscape with absurdly many possible vacuum states, each one giving different low-energy physics, different particle masses, different strengths of forces. You've got brane worlds, where what you call the universe is just one three-dimensional sheet embedded in a higher dimensional bulk. You've got many worlds, where each bubble's history branches into many quantum outcomes. You've got holography, where a higher dimensional gravity world can be exactly equivalent to a lower dimensional theory with no gravity at all. The key point is, these are not all mutually exclusive. You don't have to pick eternal inflation or string landscape or many worlds like items on a menu. They could all be describing different aspects of one deeper structure. Eternal inflation gives you many bubbles. The string landscape tells you what vacuum each bubble can fall into. Brane models tell you some of those vacuum might live on branes in a higher dimensional bulk. Many worlds says each bubble's history branches into many quantum outcomes. Holography says the whole thing might have an equivalent description in terms of a lower dimensional quantum system with no gravity at all. That sounds like a mess, but underneath the mess, there are patterns that keep repeating, and those patterns are the things you should take seriously. First, local physics is insanely regular and mathematical. The same constants and equations describe particle interactions in labs and in distant galaxies. The same quantum rules that let you design microchips match the behavior of photons from quasars billions of light years away. That level of consistency screams underlying rule set, not random chaos. Second, large-scale complexity comes from simple rules. Start from tiny quantum fluctuations in a nearly uniform early universe, add gravity, dark matter, and dark energy, and you get the cosmic web, galaxies, clusters, voids, all of it. You don't need handcrafted patterns. You feed in a small number of parameters and you get intricate structure. Third, every time observations improve, they push you outward, not inward. Better CMB data pushed you from a simple Big Bang to inflation. Thinking through inflation plus quantum mechanics pushes you into eternal inflation and bubble universes. High energy theory pushes you into extra dimensions and the string landscape. Quantum foundations push you into many worlds. Black hole thermodynamics and ADS-CFT push you into holography and emergent spacetime. None of those steps came from people trying to make the picture wilder for fun. They came from trying to fix inconsistencies, match data, and avoid infinities. At the same time, you are not free to invent any wild, bigger reality you like. There is hard data that any deeper theory has to respect. The cosmic microwave background has an almost perfect black-body spectrum at about 2.7 Kelvin, with tiny anisotropies at the level of 1 part in 100,000, and a very specific pattern of peaks and troughs in its power spectrum. Any model has to reproduce that. The energy budget of the universe is not negotiable either. Only about 5% is normal baryonic matter, about 27% is dark matter, and about 68% is dark energy. Whatever deeper picture you write down, in our bubble it has to produce those fractions, or something observationally indistinguishable from them. Quantum mechanics has worked over at least 14 orders of magnitude in length and energy scales, from atomic physics to high-energy colliders and precision tests. Its predictions about interference, entanglement, and decay rates keep passing every test. Any deeper theory has to reduce to quantum mechanics in the regimes where we've tested it, not just kind of approximate it. And the late-time structure of the universe is pinned down by galaxy surveys, the BAO scale around 150 megaparsecs, the shape of the cosmic web, and the measured accelerating expansion. A deeper model of reality still has to produce an emergent layer that looks, to observers like you, like LCDM plus small corrections. You don't get to simply declare the simulation runs differently if that contradicts the sky. So the stack of possibilities is big, but it's not arbitrary. Anything underneath has to pass through a narrow bottleneck defined by those observations. When you put all of this together, the phrase "the universe" stops meaning everything that exists and becomes much more specific. In full, what you're really talking about is this one quantum branch, produced by many worlds' evolution, inside this one inflationary bubble where inflation ended, realizing this one particular vacuum out of the string landscape, localized on this one brane or effective four-dimensional slice if higher dimensions are real, described at large scales by this emergent space-time geometry built from entanglement, with this specific mix of dark matter, dark energy, and baryonic matter, following this rule set that our instruments have partially reconstructed. That stack is what you casually compress into 3 words: the observable universe. The deeper you push with theory and data, the less it makes sense to treat that as the full story. It looks more and more like one dynamically generated, statistically selected, observationally tested layer in a reality that almost certainly goes beyond it, both outward to other bubbles, branes, vacua, and branches, and downward to more fundamental quantum informational structures. So when you look up at the night sky and say, "This is the universe," be precise about what you're actually seeing. You're looking at one tiny, bright, extremely well-behaved slice of a stack that is probably larger, stranger, and more layered than anything human senses or human storytelling were ever built to handle. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.